Hello, welcome to watch my presentation on variational model and deep learning fused medical image segmentation methods. My name is Ma, and I'm from Nanjing University of Science and Technology. First, let me briefly introduce my research background. I got my bachelor's and PhD degree in Nanjing University of Science and Technology, majoring in applied mathematics. I visited the Ma-Variational lab at University of Toronto for 6 months in 2019. My research interest lies in the interdisciplinary areas of medical image segmentation, mathematics, and deep learning. This is a brief list of my representative work. I've preferred to do fundamental studies, and my work has received more than 3,000 stars on GitHub. Following, I will present 4 segmentation work during my PhD. Let me start with a brief background. The main goal of segmentation is to delineate the region of interest from medical images, such as the organs, the lesions, and the vessels. Segmentation has many applications in clinical practice. For example, we can use the segmentation results for quantification of anatomical structures, diagnosis and disease progression, and treatment planning. In a word, segmentation is a core technology towards precise medicine. However, medical image segmentation is a challenging task. For example, in general, we only have limited labeled data to develop a machine learning model. The segmentation targets may have fuzzy boundaries. The images may have low quality, such as low contrast artifacts, blurring, and so on. We also need to deal with the fusion of multimodality images. Last but not least, we expect the segmentation methods are explainable. Because of its clinical importance and difficulties, medical image segmentation is an active research field. The two figures are the word clouds of paper titles in MICAI 2018 and 2020 accepted papers. It can be observed that segmentation is one of the high-frequency words. This is a rough timeline of segmentation methods. Before 1980s, segmentation is usually conducted by heuristic methods such as thresholding, ridge-going, and watershed. After 1980s, with the development of variational models, segmentation is often regarded as an energy functional minimization problem. In general, we will first build an energy functional regarding the segmentation contour, then we design optimization algorithms to minimize the energy functional. With the increase of data and the computing power, segmentation enters deep learning area. Many segmentation networks have been proposed, such as fully convolutional networks, UNet, DeepLab, VNet, and so on. Let's compare the two kinds of segmentation methods. Model-based segmentation methods are explainable and transparent. They do not need large training set. However, they are sensitive to initializations, and they require many hyperparameter tunings. Deep learning based methods have powerful representation ability. They are fully more automatic in touching phase. They However, they rely on large training set, and the whole pipeline are in general a black box. Uh, so we can find these two kinds of methods are have many complementary points. In this presentation, I'd like to share 4 work during my PhD. First, we create a characteristic function-based formulation for geodesic active counter model and design a fast algorithm for the new model. Then I will present 3 work about combining variational models and deep learning methods for more accurate, data-efficient, and robust segmentation. The first work is characteristic function-based geodesic active counters, which was collaborated with Dong Wang, Xiaoping Wang, and my advisor Xiaoping Yang. The main contribution is to make the geodesic active counter model simpler and faster. Basically, there are 3 types of counter representation methods. First, we can use the parametric curve to represent the contour. It is computationally efficient, but it cannot adaptively handle topological changes, and it has poor stability. Level set is a popular counter representation method. It can adaptively handle topological changes such as contour splitting and merging. However, it needs to solve a high order partial differential equation, so it suffers from high computational burden. Moreover, it needs special designs to stabilize the curve evolution, such as reinitialization or adding additional penalty term. In contrast, characteristic function-based counter representation has all the desired features. Thus, a natural question is how to use a characteristic function to represent the geodesic active contours. Our motivation is based on this work. Miranda et al. Proposed a characteristic function-based approximation to the region boundary. Let me give an intuitive explanation. We want to diffuse the heat from the outside to the inside. As we know, the diffusion of heat can only be on the boundary. Thus, in a very short time, the region of heat diffusion can be used to approximate the boundary. This idea has been incorporated in region-based active contours. In this work, we proposed this new characteristic function-based geodesic active contour model. The level set-based geodesic active term corresponds to this term, and the error term corresponds to this term. It's easy to say that the Fable set is non-convex in the original functional minimization problem. So we relax the Fable set to its convex whole, we can prove that the relaxed problem is equivalent to the original problem, in the sense that if U star is a solution of the original problem, it is also a solution of the relaxed problem, and vice versa. Next, we derive an iterative method to solve the relaxed problem. It's easy to verify that this energy functional is a concave functional, using the fact that the graph of the concave functional is always below its linear approximation. So we minimize the linearized functional based on the sequential linear program, because the minimizer of the linearized functional can give a smaller value in the energy functional. Finally, the derived algorithm only have two main operations: convolution and thresholding. We termed it as iterative convolution thresholding method. Furthermore, we can prove that the total energy is decreasing during the iteration. Compared to the level set method, the proposed characteristic function-based method enjoys following advantages. First, it does not require the additional regularization term or reinitialization. The level set method usually need an auxiliary regularization term to maintain the numerical stability, while our algorithm is intrinsically stable during iteration. Second, our method has fewer hyperparameters. It can be found that the level set method has 6 hyperparameters, while our method only have 2 hyperparameters. Third, our method has less computational burden and easy to implement. It can look when we compare the gradient descent flow, we can find that level set method need to solve this high order PDE, while our method only the main operations in our method only contain convolution and thresholding, which is very easy to implement. We first apply the proposed method onto static images to so that using characteristic function can also handle the topological changes such as the merging and splitting. Both our method and level set method can achieve the same segmentation results. However, our method is much more faster than the level set method. We also compare the energy value change with the iteration. It can be observed that our method can converge fastly. We also verify the efficiency of our method on 3 types of medical image segmentation tasks, including biopsy node ultrasound image, COVID-19 CT image, and liver tumor MR image. Both the two methods achieve similar average depth, but our method requires fewer iterations and costs fewer run times than the level set method. In the second work, we aim to embed the object global information in CNN to obtain more accurate segmentation. One of the main payoffs of current segmentation convolutional neural networks is that they rely on local appearances learned on the regular image grid without consideration of the object's global information, which may lead to inaccurate segmentation such as the isolated outliers. This paper aims to embed the object global information into a learning framework. First, we employ a level set based object representation, which can enable us to explore the dependency between pixels. Looking at this figure, small changes of the binary mask only affect local points. Well, the small change only can globally affect the level set values, resulting in large errors. Thus, level set measured representation is more sensitive to the small segmentation errors. Furthermore, we developed a level set regression network for image segmentation. The network employs a typical encoder-decoder network as a backbone. The expected output in the final layer is a level set function predicted phi. The red and green contours represent that denote the predicted segmentation and ground truth contours, respectively. At the end of the three at the end of the network, three branches are used to guide the learning. The first branch is supervised by segmentation ground truth, which guides the probability map as close to ground truth as possible in terms of death loss. The second branch is the proposed geodesic active contours, which can drive the zero level set counter of the predicted level set function towards the image boundary so as to obtain lower energy. The third branch aims to guide the predicted level set function to be close to the ground truth by the widely used L1 loss. During training, all three branches are used, while only the first branch is used to generate the segmentation during inference. To investigate the individual impact of different loss branches, we train the level set function regression network with different branch combinations on both left atrial MR and pancreas CT dataset with 5-fold cross-validation. Results show that dropping any loss branch will decrease the performance. We also compare with SOTA learning actual control methods such as level set loss and actual control loss. And SOTA boundary error reduction measures. The proposed measures achieves better performance, especially on the boundary-related metrics. These figures show the performance distribution of the 7 compared methods. The proposed method has more compact distribution, and the outliers are significantly reduced. We also compare with SOTA methods on 2 popular segmentation challenge datasets. Our method can still achieve better or competitive performance than other SOTA methods. Currently, we are using the model to help radiologists segment liver metastasis. Compared with manual segmentation, our method can save more than 50% time. In the third work, we aim to learning with unlabeled data when only limited annotations are available. Labeled data is very expensive because they cost lots of time and efforts of medical experts. Thus, we can only obtain limited labeled cases in many clinical applications. On the other hand, unlabeled data is relatively easy to obtain. Thus, a natural question is how we can explore the value in unlabeled data. For example, annotating a 3D COVID-19 CT scans on average costs about 6.5 hours, which is very labor-intensive and time-consuming. Thus, in the early days of the COVID-19 break, radiologists are busy with patient diagnosis and treatment, and we can only obtain limited labeled cases. In such situation, we need to develop an effective method to leverage unlabeled data to improve the COVID-19 infection segmentation performance. We proposed the regional active counter-regularized semi-supervised learning framework for COVID-19 infection segmentation. It contains 3 steps. In the first step, we train the segmentation network with few labeled images. Then we segment the unlabeled image by the trained network and obtain pseudo labels. The naive pseudo labels usually have low segmentation quality, such as under segmentation. To improve the quality of pseudo labels, we regularize the pseudo labels by the region scalable fitting active control model. Finally, we update the network with both labeled images and unlabeled images with the regularized pseudo labels. This is the region scale fitting model, and level set is popular representation. However, level set method is not efficient, so we introduce a characteristic function-based fast algorithm to optimize the energy function. The main operations only convolution and thresholding. Before applying the regional active control model, we use 2 chip pre-processing. First, we exclude the background by low mask. The low mask can be easily obtained by the publicly available pre-trained model. And then we remove the vessels by Hessian based vessel filter. Figure 3 represents the intermediate result during the counter evolution. We can find that with only 10 iterations, the algorithm can converge and the quality of pseudo label is improved. We apply the proposed method on a small COVID-19 CT benchmark dataset with 20 cases and a large-scale COVID-19 CT dataset with 860 cases, and compare with 2 popular pseudo-label-based semi-supervised segmentation methods. The proposed method outperforms the other methods in offer matrix. From the visualized examples, many heterogeneous regions are segmented by our method, and more accurate effects and contours are obtained. Finally, we built a statistical atlas to show the spatial distribution of infections in early COVID-19 patients. Blue regions correspond to the high incidence areas, which means more than 60% patients have infections in these areas. The we can also find that the incidence is different between the two lungs. In particular, the incidence in right lung is larger than in left lung. The dorsal and the dorsal subpleural lung is the most commonly involved region. The last work is to deal with multimodality segmentation for head and neck tumor segmentation. Radiation treatment planning for head and neck cancer involves careful delineation of the tumor target on CT images, often with the assistance of from PET images as well. Look at this example. CT image can provide clear boundary information. For example, in this part, well, the PET image is not blurring in this part. On the other hand, PET image can provide location information, which can help us to quickly identify the suspicious lesions. So the question is how we should fill the complementary information in CT and PET. And also we want the segmentation method is fully automatic. Our key idea is to embed weak boundary information, location information, and price in a variational framework. We first use a two-channel unit to obtain initial segmentation. We concatenate the CT and PET image as a joint input. The network is trained with the unweighted sum between depth loss and top K loss. We add the top K loss because we want to let the network pay more attention on the hard work cells. Then we train multiple units with random initialization to obtain multiple segmentation models. The final segmentation is the average of the multiple predictions. Then we define an uncertainty score to measure the inconsistency between each single prediction and the ensemble prediction. The higher of the uncertainty score, the more inconsistent between them. Instead of optimizing all the testing cases, we select the cases if their uncertainty scores are over 50%. We design a hybrid active counter model to define the cases with high uncertainty scores. It contains three terms: CT image-based A term, PET image-based region term, and CN probability map-based prior term. We also design a faster algorithm to minimize the energy functional. We can also theoretically prove that the total energy is decreasing during the iteration. In the experiment, we first verify that using multimodality can obtain better performance than only using single modality. Furthermore, the proposed hybrid export counter model can significantly improve the segmentation results. We also applied our method on hacker challenge in MICAI 2020. Our method ranks the second place on the final testing leaderboard, which is very close to the first place. Okay. In this presentation, we saw three paradigms to combine traditional variational models with modern deep learning methods, which can obtain more accurate, data-efficient, and robust segmentation results. Uh, there are there are still lots of open questions in medical image segmentation. In the future, I'd like to explore the fusion of theory and prior knowledge. The theoretical foundation of theory, especially for the loss function landscape and the uncertainties in medical image segmentation. Uh, Finally, we also organize an organ segmentation challenge in MICAI 2021, different from many of the existing segmentation challenges that only focus on segmentation accuracy. Our challenge focuses on accuracy, efficiency, and generalization ability of the segmentation method. Currently, it is still open for registration. We are looking forward to your participation. That's all. Thanks for your attention very much.